Hi again. As we discussed in the last video, the potential function and stream function, they both satisfy the Laplace equation in potential flows. And this is when the potential flow we are dealing with has these two conditions together. It's a 2D flow that is both irrotational and incompressible. We also noticed that we can actually use the idea of complex numbers in 2D flows. So every point in our 2D space has a coordinate x and y that we can construct a complex number z from that, x plus iy. And in polar coordinate system, its representation is r multiplied to exponential of I theta. Then it was this magical introduction that really helped us to progress, which was the idea that we can define something called complex potential function, or WZ, which is the normal potential function phi, which is varying in a space, so it's a function of z, plus the imaginary number I multiplied to c, which is also varying with z. So this definition, which we call this complex potential function, was helpful because once we defined this complex potential function, we actually saw that the conditions of the Laplacian of phi and c being both 0 plugged inside this satisfies what we called Riemann-Cauchy conditions, or so you can go back to your notes. And that meant that WZ is indeed analytical. And this was an important result because what we can right now do with WZ being analytical is the fact that it means that once you find a complex potential function, W as a function of Z, you can take its derivative. So that would be d of phi plus I psi dz. And indeed, since dz can be anything in complex numbers, remember you can approach a point from different paths. So you can approach it from this path, which has dz being equal to dx, or you can approach the point from this path, which has dz being equal to I dy. So you can approach the same point from different paths, but you should basically, when the function is analytical, no matter which trajectory or navigation you approach a number, the derivative will be the same on all different trajectories. What would allow us to actually calculate this. And d phi over dz, if I use dz being actually dx, would give me d phi over dx, which by definition is the x component of velocity. And then I have I and d psi over dx, but d psi over dx is negative vy. So I will get a negative I multiplied to vy, which will be vx minus I vy. So we see actually an interesting identity here. If you find what is your complex potential function, just take the derivative of that relationship with respect to z. What you get as a complex number is real component would be the x component of velocity. Its imaginary component would be the negative of the y component of velocity. We showed that these ideas are important, and then we introduced many different functions, complex potential functions, for different group or different sets of solutions that satisfy potential flows. The reason we did that was the fact that each of these have different shape for streamlines, and we know that in potential flows it's very important to find the right solution that gives us some streamlines that follow exactly the shape of the object that we are studying. It's important to always know that in potential flows, that's really our final goal, to find a simple solution to potential flow that will give us at least one streamline that follows the trajectory or the shape or the profile of the object that we are studying, so that the flow will smoothly follow that trajectory. And we notice, for example, there are a class of, as an example, there was this class of flows that we called corner flows. And we noticed that their general form of W of Z is defined as A multiplied to Z to the power of N. And for the case of N equal to 2, if this is my X and this is my Y, we notice that the shape of flow here becomes something interesting. Two streamlines are indeed the vertical line and the horizontal line. So two streamlines are basically the Y and X axis. But there are also other streamlines that go very much like this. So this is one streamline, this is another streamline, and this is a different streamline. And we also noticed, because of the fact or the way that stream function and potential function are defined, lines of constant stream function, which are streamlines, are always orthogonal to lines of constant potential function, which we call isopotential lines. So if you find the streamlines for a flow, you can always find the lines that are locally orthogonal to streamlines, and those would be your potential lines. So you clearly see that there is a diagonal line that goes like this, and there is another line of constant potential that is always orthogonal to streamlines at every point is hitting the streamline. So we had this idea, and these ideas were useful because at least from green here, which is streamlines, we could, just by looking at the shape of the streamlines, we could get a clear idea about when the streamlines are becoming, the spacing between streamlines becomes smaller and smaller. That suggests that fluid elements are getting more and more acceleration as they are entering that region of tight streamlines, because of the fact that the volumetric flow rate between two streamlines remains constant. Just the shape and the profile of streamlines can tell you a lot about the kinematics of the flow. Potential lines, or lines of constant potential, which are called isopotential lines, and they are also interesting, but it's always, at least for me, more intuitive to think about the streamlines, because they actually follow the trajectory of fluid elements in steady state flows in an exact manner. So you can clearly see what will happen to a fluid element as it's entering this flow field according to the streamlines that are described here. But you can you don't really need to calculate both. As I said, once you have one set of the lines, the other set can be easily found or drawn by just noticing that these two are always mutually orthogonal on each other. So this was a very short recap of most of the basic concepts, basic mathematical concepts we use in potential flows. As I said, the idea is we introduce many different complex potential function to you. You have a PDF page available on the website that has all these different functions introduced with their corresponding mathematical expressions for a stream function and potential function, and the shape of streamlines and potential lines of constant potential or isopotential lines. They're all given to you. And the idea is, after you are introduced to this zoology of different solutions, combine them together in a manner that is meaningful, which should satisfy the Laplace equation. But since Laplace equation is linear, that means that any linear superposition of different solutions would be, again, a valid solution for this type of equations. But combine them in a meaningful manner that would, and that's the most important thing, that would mimic the shape or the profile of the object that we are interested. And that's the example we will do in the next video. We will go through the review for flow past the cylinder, and you will see that combining two solutions, we will get what is actually a nice potential flow solution that mimics the shape of the cylinder. And we will do that together in the coming video.